Hi, welcome back. I'm Flavio, and in the last video we left with a long explanation regarding the first spark gap wireless power experiment we performed. Basically, in that experiment we used a transmitter circuit which uses as electrical switch a spark gap, and a receiver circuit composed by an identical one, except for the fact that the receiver doesn't need the spark gap and can be used to turn on an old fluorescent light. But here's the catch. What if the receiver is placed much closer to the transmitter? We shrink it a bit to be able to put it inside, and then change the inductance-capacitance ratio drastically while keeping it close enough to the same resonance frequency, maybe with something like this. With not tens but hundreds of turns on it, maybe even around 1000 if not a little more. But now we have a coil with an output which voltage is gonna be huge, too much to use a conventional capacitor. So what we do now to tune it to the same frequency of the transmitter, what will happen? Because this coil has so many turns, its voltage rises dramatically, and that's why normal capacitors simply cannot survive easily here without going boom. Well, we first consider the fact that we can just put here a coil and fine-tune it at a certain frequency without adding a capacitor. This is because the resonance frequency comes with this formula. And as you can see, it requires both a coil but also a capacitor though. Instead, the voltage, again, is huge and very difficult to manage with a classical capacitor. So what we do? In short, we need a capacitor that won't instantly explode at hundreds of thousands of volts. Well, you have to know that a coil or inductor alone have a resonance frequency due to some parasitic capacitance, but we can't control it, and also it's not gonna be probably the right one. So we have to add some capacitance somewhat, while at the same time handling hundreds of thousands of volts. Before going on, I have to tell you a little secret. You probably know this formula, but this time it's not gonna help us. I mean, maybe you probably want to say now, why? Well, this formula works great, yes, but not always, because it's too specific, and also because it's an approximation. What I mean is that in reality you can actually store a small amount of charge on a single surface on the condition that it's big enough and insulated from everything else, while building up some actual voltage on the surface compared to ground or the environment. This is just a basic concept coming from electrostatic basics theory, which tells you also that you can just expose a metallic insulated surface to some electric charge and pass some to it, without necessarily having the second surface. And this is exactly the principle Tesla used when designing high voltage resonant coils. Now, what I just told you is the key, because the idea is, okay, we can practically and easily just use classical capacitors because they would break down immediately, but we can still use big metallic and curved closed surfaces on both sides to give charges a way to accumulate on both sides of the coil I built. Now, what we all have to do is to put on both sides of the coil these hollow spheres made of steel or other conducting materials, each one carrying a single surface capacitance which can be calculated numerically with the following formula. We can alternatively use hollow metal toroids, but the calculation of the single surface capacitance for them is more complex. Anyway, another key ingredient here is the mutual magnetic coupling, because like in a transformer, the primary coil produces a rapidly changing magnetic field, and the secondary coil intercepts part of that field. The amount of shared magnetic field between them is called the coupling coefficient. If the coupling is too weak, the secondary barely receives any energy. If it's too strong, the resonant behavior gets though distorted. Tesla coils works best when a moderate coupling enough to transfer energy efficiently while still allowing the secondary to ring freely, typically something between 0.2 and 0.3. So, let's now put together everything we know. We have a high-frequency pulses coil, coupled magnetically with a receiver one, with many more turns compared to the transmitting one, resulting in a hugely enhanced voltage on the output. Also, the fact that the resonant frequency of the two coils is close enough is essential for the best possible performances of the apparatus. Basically, we just got, at least to some extent, the double Tesla coil. Or, in simpler words, a primary coil sending pulses, and a secondary coil boosting the voltage, just like a classical Tesla coil design. Now we put everything together and let's see what happens. Let's first add a couple of pointy terminals from where the lightning bolts will come from. Now what's interesting to observe is that the lightning bolts from both sides don't actually touch each other, but rather just break down half air with the shear force of the electric fields produced. They follow the electric field lines, not each other, which is why they appear to miss each other. Now, you could ask, okay, but if you're arguing that this is a Tesla coil, can it turn on wirelessly a fluorescent light lamp or a neon? Well, the answer is absolutely yes. In the next video, we'll go with another experiment on this line. See ya!